Welcome back to Classroom. My name is Mr. Wong. In today's lesson, we're going to be looking at the qualitative analysis of the diffraction of light. We're going to use the diffraction gratings using the following formula to predict the distance of the interference patterns and also predict how far they are based on the wavelength of light we use.
Diffraction grating. This is what it looks like. Okay, looks might be slightly deceiving. We might have this at school, and we can probably try out the experiment as well. So, what is this thing? Now, a diffraction grating separates colors or light into its colored components. If it's monochromatic, so if we only have one wavelength of light, then it will just separate it out accordingly. Okay? Inside this grating, you might not see it, but there's some really fine little parallel lines that act as little slits inside the diffracting grating, and it actually spreads the light into different positions. If you compare the diffraction grating and a double slit experiment, you can see there's a very big difference in the sharpness or resolution of the image. So the bright fringes produced by a diffracting grating are much more narrow than a double slit experiment. Okay, so it's a lot finer, and the reason being is obviously because the lines are a lot more narrow. So difference between diffraction grating and double split, the maxima is a lot more narrow, and it's a lot more sensitive, so you can do some more accurate calculations on that. Double slit, you can see that it's a little bit more spread apart. Intensity will stay the same if you're using the same wavelength of light. Okay, another way, diffracting grating is a set of accurately ruled lines on a glass that produces sharp patterns of maxima and minima. So this is really useful with our analysis of the equation d sine theta and lambda. Okay, so that's helping us to work out the path difference between the light and what's happening there. So really nice sharp patterns. How does it work? So you'll have equally distant parallel lines engraved on glass. Okay, these will act as the slits that allow the light to go through. Now, for this to work, the wavelength of light you use must match the gap of the slit. So if the slit has a gap of, let's say, 400 nanometers, so it has a separation of 400 nanometers, then you must use a wavelength of 400 nanometers or slightly less than that, or else you won't get that pattern. Or it could be slightly bigger. I'll have to check on that, but it needs to be close to this the separation of the slits. The more slits you have, the sharper the image. And so these lines break the wavefront and cause a diffraction pattern to occur. If we look at the calculations of this, so let's say we have a white light source and we run it through a diffracting grating. The center will be white, and then you'll have the rainbows forming there. If you have a look here, if we have a look kind of the displacement of red light and blue light, you can see that blue light being the less energetic, or being the more energetic and lower wave, it actually displaces less, so it has a smaller diffraction angle than the color red. So the longer the wavelength of light you use, the greater the diffraction you'll see from the center point in terms of the angle produced. And we can see that again. So the diagram shows how different or how diffraction splits the wavelengths. Note that the longer wavelengths diffract more than the shorter wavelengths. Okay, so red light will diffract more than blue, so the colors will separate. If the light is white, then a full spectrum of the rainbow showing you the equal maximums and minimums will show as well. Either way though, you'll see a similar interference pattern here. So if we did a single split experiment, we kind of look something like this. And then what we have down here is the double slit interference. And so you can see it will give you the same shape, essentially. So if we just kind of compare these, this is a double slit experiment. This is with a diffracting grating, the interference pattern you see. This is if you're using a single slit interference. Notice they kind of all show a similar shape. Now, diffracting grating has narrower lines, but they essentially show the same amount of intensity graph. So kind of, if we're looking at the single slit and it kind of looks like this, in the diffracting grating, they kind of also show the same shape. Mind you, my diagram is definitely not as nice as that one, but so it shows a similar kind of diffraction.
Another thing when you are using a diffraction grating, you might notice these labels here. It says 1000 lines per millimeter. So obviously, what does that mean? What that actually tries to explain to you is if you have 1000 lines per 1 millimeter, it's essentially saying that in 1 millimeter, you have 1000 lines of slit separation. So what that means is if I try and convert that into meters, 1 millimeter is essentially 1 times 10 to the power of 3 meters, so 0.001 meters. Okay, so in that tiny bit of space, there are 10,000 little lines splitting up the little grating here. And if I do that calculation, it means there is a slit separation of 0.0000001 meter, meaning essentially that the gap between one slit to another is about 1 times 10 to the power of minus 6. And that's how we produce these incredibly fine lines with a diffracting grating, which you can't get from a double slit experiment. Okay, now that we've gone through the theory of how diffracting gratings work and how to do the measurements for the different number of slits, let's go through some calculations. So I have a diffraction grating that has 5,000 slits per centimeter. So just keep that in mind. We need to actually look at that distance in separation. So the distance in separation is we have for every 1 centimeter, so 0.01 meters, we have 5,000 slits. What would be the angular separation? So we are trying to find theta here of red light with a wavelength of this particular wavelength that again needs to be converted into meters, so 10 to the power minus 9 meters there. Okay, so we have blue light with a wavelength of 420 nanometers, and it's asking us for the first order of maxima. So if you recall with the appearance of an interference pattern, we have the central maximum point. So this is the brightest point here, and that is known as N0. Okay, and then our other maxima here, that's a bit less bright, and N1 there. Okay, so that's what we have. We are trying to find this one here or this one here. Now the question, or for this question, we're going to apply the interference pattern formula. Don't actually know what we call this, but we use it to look at interference patterns, so we'll just call it the interference pattern formula. Obviously, you can use it for diffraction patterns as well, because they give a similar type of shape, but obviously for diffraction it's a bit sharper than interference patterns. So D is the separation of the slits. We've done that calculation here. It's a value of 10 to the power of, or 20 times 10 to the power of 6 meters. So that's what we have here. And from there, we can then use the formula to calculate that. So maxima is 1. So if I do that calculation there, so 20 times 10 to the power of -6, sine theta, theta being the angular separation we're trying to find, 1, or n is 1, because that's the first maxima. And then we're going to use the wavelength. I'm going to use the red light first, and then we can just follow with the same substitution with blue light. So that's what we have here. So theta is the sine inverse of 1 multiplied by 632 times 10 to the power of -9 over 20 times 10 to the power of -6. And it's approximately 1.8 degrees for the red light. So that's the degrees of diffraction from the center point if we were looking at red light here. If I was looking at blue light, so we do the exact same substitution, but instead of using 600, we're going to use 420 times 10 to the power of 9 over 20 times 10 to the power of 6. We get approximately 1.2 degrees for the blue light. So what you can see here is the diffraction of blue light as a angular separation is smaller than red light for the same first order maxima, as you can see here. Okay, so like we said about the diffraction patterns, the main difference between a diffraction grating and interference or general double slit experiment is that obviously the diffraction grating has a lot more little separation splits that would break the wave of the light further away from each other. So if we think about the center point as that white light here, we can break it into the different colors of the rainbow. So the first order rainbow, second order rainbow. Remember, when we see this rainbow color here, that's because of some form of constructive interference within for the particular rainbow colors of the same type. So we have violet here, blue, and then red, which makes sense because this image is matching up the calculations we did just there. We said that the angle, so the angle for the blue light from the center was smaller than the angle produced by the red light. That's consistent to what we said. Okay, so a couple more calculation questions. We have a diffracting grating with 12,000 lines per centimeter. So if that's the case here, it's 0.01 over 12,000. That gives me exactly 8.333 repeated, 7 to the power, or 10 to the power of -7. We have a separation of the bright bands of 24.5. We want to know what's the wavelength of the light. Okay. So we're going to use the formula d sine theta equals to n lambda. Now n in this case, assuming that it's from one bright line, we can assume that it's the first maximum. So again, we can use 1. So d is 8.333 repeater 10 to the power of -7 sine theta equals to 1 multiplied by the wavelength. That's what we want to find. Theta here, is 24.5. Okay, so we divide both sides by 1, and we find that lambda is approximately 346.5 or 346 times 10 to the power of -9 meters. Now this is a very short wavelength of light. It's actually within the UV spectra, so we wouldn't actually be able to see it. We have a grating in a spectrometer. Spectrometer is obviously a device that's used to split different colors of light. Has a length of 2 centimeters and contains that many number of lines, 10,400. So D is 0.02 divided by 10,400 lines. It says find the third order diffraction angle. So that's 3, and 3 we're trying to find, with a wavelength of 540 nanometers. So we want to find angle. So D sine theta equals lambda n lambda. Just to change it up a little bit, we'll rearrange the values first. So it'll be n lambda over D. So that is sine inverse of 3 multiplied by the wavelength, 540 nanometers. So 9 to the -9. Okay. And then we have our distance in separation, which is this number here. And the number I got was 1.923076923 times 10 to the power of -6. And that rounds us off approximately to 57.4 degrees. Okay, so that's how you do these two calculations here. Okay, our next question is actually a multiple choice question. It says we have a monochromatic, so wavelength is constant, or the same wavelength of light, strikes a double slit and produces a bright and dark band on the screen. Light from slit S1 travels along path 1, and light from slit 2 travels along path 2, produce the dark fringe as shown. What is the difference in the length between P and P2? So if we have a look here, our center bright band, from the looks of it, is this one here, N0. Okay. So our next bright band is N1. Remember, N1 is the same thing as saying N lambda if it's for constructive. Okay. So that's just one wavelength. For destructive, it's N minus half lambda. So this next bright band that we have here is N2, which means in between N2 and N1, the wavelength produced is N 1.5 lambda or 3/2 lambda. So the answer in this case is C. Remember, the idea is very simple in terms of how destructive interference occurs. So we have one of the waves here, and if I want to draw an image of the wave being half a wave behind, so if it's half a wave behind, let's say starting from this point here, so it's half a wave behind because this whole line is a wave. It starts from here, goes up, and then comes back down like so. So what you can see is this point here would cancel out this point here, and same idea, this point here would cancel this point here, and so that's where the destructive interference occurs. That's what we mean by the half. It means the wave is half behind the other, or so to speak, 90 degrees behind. So this was taken from the additional sample paper, and if you can actually see here, it was graded as a band 4 to 5 response. So if you could do that, brilliant. If not, have a look again of the logic behind how these bright bands and dark bands are formed. Okay, next question. Anna and Bo carried out an independent experiment to investigate Malthus's law. Based on the two graphs, which of the following is correct? A, Anna has taken more measurements, but Bo has used a better data range. B. Bo's graph is more precise as the angles in Anna's graph are too small. C. Anna's graph is more valid as Bo's graph shows a straight line relationship. Or D. Anna's measurements are more reliable than Bo's as a line of the best fit cannot be drawn. Okay, so in this context that we have here, if you actually compare the shape, then obviously Anna's one, because if we're talking about Malthus's law, we are expecting technically a cosine graph as well. That's what we have in degrees here, and that's what we have in terms of the intensity. The correct answer in this case is actually A. Anna actually has more, or Anna has more data points, as you can see here. 1, 2, 3, 4, 5, 6, 7, in comparison to Bo, who has 5. However, Bo's has a greater data range from 0 to 80, while as Anna's is from 0 to about 12. So the range is a lot smaller. And so that means that the range is better because there is obviously a bigger data set to work with. In terms of bands, that's about 3 to 4. So that's what we have there. You can also try some of these past paper questions. Links are in the descriptions below. Have a go at doing some more calculation questions related to interference patterns. And that takes us to the end of the lesson. Thank you so much for joining. Hopefully by this point here you have a better understanding of the difference between a double slit interference pattern with a diffraction pattern. And also you are a bit more confident in performing those calculation type questions. If not, try those past paper questions. But until then, I'll see you next time. Thank you so much for watching.